So I'm going to start. I'm going to start with problem 820. That was the one we did, or at least started. And for that one, has this. And I'm going to call it DS in mind. The only thing he really wants is with the input impedances to DS. I'll get to that in a second. Then he has two resistors here, 2 ohms, or 2 impedances, and this is going to be minus J4. Then he shows this on the primary side. And on the secondary side, and this is a 2-to-1 ratio. And then I'm just going to draw it this way, straight down so you can see it better. He has minus J2, and he has 1, and then he has another resistor of 3, and this is where he has V out. Now, so this is the circuit that he has in the book. And let me explain something to you. When you're doing problems like this side to the left where the source is, or if the source was on the right, is called the primary. The source where the load is, or where the voltage, or basically where you want the information, this is called the secondary. It really doesn't matter. In the long run, it has no bearing at all. The key thing is this ratio. This side is N1 where the primary is. This is N2. And the ratio of N1 to N2 determine everything about the reflected impedance from the load side to the primary side. And basically, it tells the tale that you need to. Now, when you're dealing with this, and I'm going to put this here, on this side. This is called I1. Now, I've done this before. And the voltage on the primary side is called V1. It's just a matter of standard convenience. It means nothing more than that. On the secondary, there's going to be a voltage V2. Now, because that looks like a voltage source, the current is assumed out of the secondary. I have to say this. If you ever have to deal with magnetically coupled circuits that will have the exact same topology with one exception, instead of seeing a turns ratio 2-to-1, you will see a little arrow that will have like J4, J10. Has anybody done magnetically coupled circuits at all? Some of you, if you have rail guns or anything like that, I think mechanical engineers probably have something with magnetic, or maybe magnetic thruster, something like this. If you deal with that kind of stuff, you'll see magnetically coupled circuits. If you deal, this is not for you, but if you do in the future ever deal with magnetically coupled circuits, the current is in the opposite direction. It's into the dot. I don't like it. It's not my choice. That's the standard they've created, so I have to deal with it. But this is the standard we deal with. This V2 looks like a source. Current I2 is going this way. Now, that said, the ratio of V1 to V2 is equal to N1 over N2. I'm going to make that absolutely as clear as I can. As shown in that drawing, it's also on OneNote. How many have looked on OneNote and seen that transformer drawing? Very few of you. Please do. And make sure you understand it well. Try to do these problems before the next class. And if you have any questions at all, you can't get the right answer, don't understand something, bring it to my attention. That's critical. Typically what happens is they'll make one of these 1. Like N1, you'll see in the book 1, and then you'll see 2. That doesn't give you the exact number of turns, but it gives you the ratio of turns. For every 1 on the primary side, there's 2 on the secondary. You all follow me? It could be 100 turns on the primary, 200 in the secondary, it doesn't matter. The ratio is the only thing that matters. So I put that there, but I should have put 2 to 1. Here they have 2 to 1. Now the next thing is, for currents, you can think of, I do it this way. I'll put N1 I1 is equal to N2 I2. But really that means I1 over I2 is equal to N2 over N1. Now I'm going to make a comment on this. This is the way I remember it. I just use that and I get the ratio. You'll notice for the currents, the turns ratio of primary to second is inversely proportional to the actual currents themselves, not directly proportional. For voltage, it's directly proportional. With voltage, and I'm trying to tell you how I think about this, whatever side has more turns, this has more turns. There's more voltage here than there is here. That's simple. That's the only way I think about it. For current, it's opposite. Whatever side has more voltage has less current. Now, there is one constant that I really don't want to dwell on too much. But if you took V1 times I1, that is a common, measure of power. Do you agree with this, class? V1 I1 on this side is V2 I2 on this side. What that is implying is there is no power loss in these transformers. They are considered ideal, but for the most part, in the real world, your assumptions are ideal transformers. If these transformers have any significant loss, they're really of no use to you, and it's called a magnetically coupled circuit. I'm trying to be frank about this. I can always, in the back of my mind, I keep thinking about your MEs, aerospace engineers, industrial engineers. What could they encounter that has a non-ideal transformer? There might be something, but I can't think of it. I'm just trying to tell you how. If I'm teaching this course, I'm trying to teach you in a way that best benefit you in the real world. I'm not going to give you a bunch of stuff that you'll never see for the rest of your lives, but this is important. And mechanical engineers, for sure, you guys are going to use this stuff, I'm sure of that. Anyway, now that's the ratios of voltage and current. The next one is impedance. And the way we get impedance is always going to be, if you look at this right here, I guess I can do it right, I can show you. If I take a look at impedance in the primary, all right, this would be Z on the primary side. Well, that is equal to V1 over I1. And what I'm saying is this. If you somehow, think about this, if we could measure V1 and we could measure I1, the ratio of that voltage to that current would be the impedance here. Do you agree with that, class? So I'll just break out a transformer and say, I'm going to try to get rid of anything else that will affect this. And by the way, I didn't say this, but the dotted terminals are where the current goes in or out. I think I said this before, both going in, and that was for a magnetically coupled circuit. Remember, current goes into the dot on the primary, comes out of the dot on the secondary. This is important. All right? So back to this thing. If this is N1, this is N2, and this is V1, and this is V2, and this is I1, and I2 is coming out, then I might as well just do it right here. Can everybody see this in the far back especially, sir? Okay. If you take a look at this, I know on the primary side, V1 over I1 would be the impedance on the primary side. I think we all agree with that. That would be the voltage and the current of that element. Now, if you look at this, well, V1 is equal to N1, N2 over N2, V2. And I1 over here is really N2 over N1, I2. I'm just trying to show you the logic, so it's absolutely clear. You cannot, I try never to give people just memorization. I listened to a medical doctor on YouTube, and she's at the Boulder Longevity Clinic. Her name is Dr. Elizabeth Urick, and she was talking about how in medical school you're told protocols, just mean what to do if this is the case, what to do, never why to do, at least for a large part, why that particular treatment would work for that particular condition. And it gets very frustrating when you're in the real world and you're trying to figure out why something doesn't work. That's a protocol approach, it's the technician's approach in our world. As engineers, you have to know the why. That's the whole difference between you and technicians that just know, if these are the things that happen, I do this. You've got to understand the reasons behind everything, the fundamental physics. That's a big, big deal in engineering. So this is the reason why. Now, if you really wanted to get into it, if you wanted to go into the fundamental physics of a transformer, we could. Well, not in this class, but you could dig down into it and see that everything is based on fundamental physics that we're doing that are absolutely observable and measurable and repeatable. So anyway, now you can plainly see this turns ratio. You can flip it and just square it up there. And then V2 over I2 would be the impedance in the secondary. Do you all see that? So when you have V2 here and I2 here, what you have is the impedance of the load. Can you all see that, class? So what I'm going to do is this. I'm going to do two things. I'll put it equal to here. This is really N1 over N2 squared. And V2 over I2, you can simply call that Z load. Now Z load is the sum of all the equivalent impedances that this secondary sees. Does that make sense to everybody? So let me give you some insights. Whatever side has more turns will have a reflected impedance that's the square of that ratio. Now let me be very clear. We're going to do this problem, but I want you to see this. Here I have a total of 3 ohms real minus J2 imaginary, right? So I'm going to just deal with this problem, and I'll tell you where I'm going with it. And you'll see. Now you'll notice this side has more turns, right? So the reflected impedance from this side is going to be magnified by the square of the ratio. More turns, more impedance, but it's the square. Because you can see that turns ratio straight. Can you all see that, class? All right, so right here, this impedance that would be measured, now let me be clear about it. If you just took that out of here and you wanted the impedance here, Zn, I would have to have 2 minus J4. That's always there. Agreed, class? So I'm going to come over here and I'm going to say Zn would be equal to 2 minus J4 plus, now it's the reflected impedance across that primary. Can you all see what I'm doing here? And that impedance would be this impedance times the turns ratio. So it's plus 3 minus J2, but the turns ratio, you'll notice it's N1 over N2. N1 is 2, right? Yes, sir.
Is there a 3 ohm resistor and a 1 ohm resistor?
Yeah, do you have your book or access to it? It's 3 and 1, isn't it, class?
2.
Or, I'm sorry, is this, I'm sorry, 2 and 1, 3 total, my bad. I'm sorry. Thank you, though, very much. All right, you all with me, class? Sorry about that. It's 1 and it's 1 ohm load, 2 ohms in series with, or sorry, 2 ohm load, 1 ohms in series with a total of 3 real. My bad on that one. You all with me? Okay. But I have to multiply it by the turns ratio and square. N1 is 2, N2 is 1, so it's 2 squared. Well, I'll leave it as 2 squared just for the notes. And for anybody that's viewing it online. Y'all follow me? That's the method. That's the turns ratio squared. So if you look at this, what is Zn going to be? Well, here the real part, that's 4. 4 times 3, 12 plus 2 is 14. And then I have what? I have 4 times, if I did this right, I have 4 times 2 would be 8, and 4 would be 12, so it'd be minus 12. I think that's right. I looked at this before I came in, or came down here, so I think that's right. Y'all with me, class? Does anybody have access to this solution? I'm sure that's right, but that's how you do this. Now that's the reflected impedance. I want to continue on with this problem, but I'm going to do something I did on Friday. I didn't have a chance to rectify what I did wrong. So, because I had that current going in. Now I'm going to put the voltage back on here. And the voltage I'm going to put, I could put Vs, but I'm going to put 100 volts. 100 volts, and we'll make sure it's RMS so we don't have to worry about anything else. Now, follow the steps. Because one person mentioned they like the procedures outlined. So, first thing is, when you're doing these problems, you got to find the input impedance to the actual source voltage. I'm not going to give you problems with 2 source voltages. That's for electrical and computer engineers, not for you. Sometimes they'll have another voltage source here and another voltage source, and you're going to have a series of things to consider that is far beyond what you need to worry about. You don't need to worry about it. All right, so first you get Z in. After you have Z in, the next thing you need to get is I in. So we need to get the current I1 in this case. That would be I in, but it would be I1. Do y'all follow me, class? You need to find the currents on the primary side, and I gotta say one other thing. Sometimes, and this is just to irritate you and make sure you know what you're doing, they may have another impedance, like these two are in series, right? But they may have an impedance right here, like maybe plus J5. Y'all follow me? That plus J5 would be in parallel with the reflected impedance. How many see that? You understand what I'm saying? They can complicate these things, but as long as you understand fundamental circuit analysis, you can do these problems. Don't let anything like that scare you. Anyway, back to this one, I want to get I1. Now, that should be straightforward. I1 would be Vs divided by Zn. It's nothing more or less than that. Do you agree? So Vs, I chose 100 volts just because I felt like it. There's no real reason. So if I take 100 volts over Zn, or over 14 minus J12, now I get I1. Does everybody follow me? I'm really trying to be clear. All right. Now, if that is I1, I'm asking you, as a class, how would you get V out? Anybody? All right, I find I2. Let's say I have I2. Now what? I know I2. Say again? Yeah, what he's saying is just 2 times I2. Do you agree with that? And so let me put that right here. I'm going to say that V out is equal to 2 ohms, because that's the output resistance, times I2. I just wrote it down. I want to keep going on this. Make sure you see this. So now it's going to be 2. And what is I2? Well, take a look. More turns, more voltage. Less turns, less voltage. More turns, less current. Less turns, more current. It's going to be up by the turns ratio. Do you all follow me? So on this side, I know that my I2 is going to be 2 times I1. So it's 2 times 2 times I1, which is this. Let me try to make that a little bigger. So it's 2 times 2 times I1, and this is I1, which is 100 over 14 minus J12. Now, I'm just going through the process. So the third thing you do, and I'll call this I1, is, in this case, I found I2. And after I2, the fourth thing is finding V out. For this problem, is simply I2 times R load. I'll get out of your way, but I'm just showing you the method. You all with me? So let's see what happens here. That's 100 volts. 100 times this is, it's going to be 400 divided by 14 minus J12. Can somebody give me that? That's going to be a magnitude and an angle, correct, class? It's going to be a complex number. Everybody follow me? So what is that? Anyway, I'm trying to be clear. And I'm not flying through this. I'll ask for it in polar. Almost always the load voltage, load current, polar. Input impedance, if I ask for anything about impedance, it'd probably be rectangular or real and imaginary. You all follow me, class? So what is this going to be? Yes, sir.
21.7 at an angle of 41.
21.7 at an angle of 41 degrees?
41.
And that's volts RMS. Now, I have a question. Listen to me. Kind of question you would get, and people sometimes panic because you didn't see this on the homework. What if I asked for the power, average power dissipated by that load, the 2 ohms? Think. Anyone? He said it, right? Take the current, I2, the magnitude of it, and square it times that resistance. Does everybody hear that? You have all the tools to know that. I have a question, second question. If I, just listen, don't respond, listen. If I asked, which I might, for the average power dissipated by the minus J2, it is average power. Class? 0, right? Now, last thing, if I ask for the complex power associated with this load. Just think, you don't respond. Well, I know complex power is V times I conjugate. Do you agree with that? Now listen to me carefully. Do we have the voltage V2? Well, we can get it, right? Whatever the how would we get it? Just tell me. We could get it by taking what? I2 times this, couldn't we? I2 times the load impedance, the 3 minus J2. How many see that? That would be V2. There's a lot of ways to get to this point. Or we could find V1 and use the turns ratio to get V2. But it's easier to just multiply the current in the secondary by the load to get it, in my opinion. Less steps. So if we have that voltage, we have the current also, don't we? So the complex power would be the voltage I2 times 3 minus J2 times I2 conjugate. Do you all see that, class? How many do? Complex power. Do you all see this? I mean, you guys know this. Are you with me on this? I'm looking at you and I don't see anything. This is like, who cares? You care because you're going to be asked this, so care. I mean, are you following me? I'm trying to show you how straightforward these problems will be, but nothing is left behind from before that isn't used again. You have to make sure you don't do complex power and forget it. You'll be asked about it. Got that? Okay. All right, that's the first problem I did. Or I wanted to finish that one. The next one I'm going to ask you how to do. Did you have a question, anybody? Any questions at all? I am doing my best to be as clear as I can about this, but I do need some, if you don't understand something, let me know so I can help, hopefully. Okay, next. next problem. This one's a little different. But it'll require you to think, but you've got all the tools to do it. I'm going to do problem 823. I'll need your help. Here, they show you VS. This is an inverse problem. They give you output information, they want input. Then they have R1 here. Well, actually, let me do it this way. This is going to be I1, and this is I'll tell you what, let me do 824. That problem, too many uncertainties. So it's VS there. I1, this is 3 ohms. Then they have a transformer. And they have this. 1, 2. Then they have 6 and 2. And they say this. They say this voltage is measured as 12 volts at 0 degrees, volts RMS. They want VS. So what they're saying is now I have this voltage on the output, that's volts RMS, but they want this voltage on the input. And that's what they're after. This is an inverse problem. You'll notice the way the dots are, they're both on the top. So this is still the primary. Y'all follow me? Even though the voltage is given is here, it's not the source voltage. Does everybody follow me on this class? All right, so this voltage would be V1. This voltage would be V2. This current would be I1, and this current right here would be I2. Does everybody follow me on this class? All right, now, to keep going on this one, how would you do it? I'm asking you. We want VS. Now remember, if you don't remember these equations, I'll put them up here right now. V1 over V2 is N1 over N2. I1 N1 is I2 N2, or better yet, I1 over I2 is equal to N2 over N1. Z primary here is going to be Z secondary or Z load, right? And then it's the turns ratios. Okay. So how would you do it? Does anybody want to make a comment? I'm not going to call on anybody, but I'm asking. Where would you start? Let's try that. Anyone? What would be the first obvious thing that you would get? Take a look at what's given. Yes, sir.
I2.
Yeah, and what would I2 be? Now, he's absolutely right. Y'all see that this current is flowing down here. Y'all with me? So the current through the 2 ohm is in fact I2. Do you agree with that? Make sure you see this without any problem at all. So what I can do is say that I2 would be equal to what? 12 divided by 2, or 6 amps at 0 degrees, and it's RMS. Do you agree with that, everyone? Can you all see that? Far back, guys? All right. What next? Think for a second. Well, I mean, we can do this several ways. Now, here's the problem. Think about what you can get and what you want to get and what you need to know. If I want VS, I can get I1 pretty straightforward. Do you agree with that? So if I have I1 times 3, that would be this voltage, right? But I need this voltage. Do you agree with that, class? We could get that voltage a couple of ways. You could get the reflected impedance times I1. Do you agree with that? How many understand that? If you have the reflected impedance right here times I1, that would be the voltage. Or I can say what? The voltage V2 would be I2 times a total of what? 8 ohms? You see that? I have a total of 6 and 2 is 8, right? 8 ohms times I2 would be the voltage V2. Do you agree with that? And if I had V2, I could use the turns ratio to get V1. So there are several ways to get the value V1 that you would add to this additional voltage right here, right? The 3 times out. But, and all of them are right. Don't think one of them is right, one of them is wrong. That, I think, happens at times in this class. There are many ways to get to this solution. It's the preference. So what I'm going to do is this. I'm going to go ahead, because we haven't done it, is get V1. Y'all follow me? So first I need to get V2. So what is V2 going to be? Well, it's what? I2, right? Times 8. Do you agree with that? It's really I2 times 8, and since I2 is 6, it's 6 times 8, or 48 volts RMS. You agree? All right, now what would V1 be based on that? You take a look. Remember, more turns, more voltage, less turns, less voltage. It's going to be less on this side. Do you agree? By how much? By a factor of 2. You all follow me on this, class? So that means V1 is really going to be what? V2 divided by 2. Look at that. Or it's 48 over 2, or 24 volts. Do you agree with that, class? Finally, to get VS here, what do we need? Now, we're right up to the closing. What do we do, class? We've got V2, or sorry, we've got V1. That voltage is what? 3I1. Do you agree with that? Do we have I1? Maybe we don't have I1. How do we get I1? Wait. Well, what happens? More turns, less current? I'm sorry, more turns, more voltage. In this case, less turns, the 1, more current by the actual turns ratio. Do y'all follow me, class? Because V1 I1 is V2 I2. So that means, and I better put it here, it's going to be 2 times my I2. And since I2 was 6, this is going to be 12 amps. And it's at 0 degrees, and it's RMS. Do you agree with that? Okay, finally, for VS, now what do we get? I can write it down. It's going to be I1 times 3 plus V1. I'm just putting down for everybody's sake. So if you're looking at the video and aren't here, because it looks like a lot of people aren't here, you'll see this. I1 is 12 times 3 is 36, but I'll put it here. 12 times 3 plus V1, which is 24. So I have 36 plus 24, or 60 volts. Do you agree, class? Do you understand the technique and why I did what I did? Because the problems oftentimes are you're trying to just have a series of steps without understanding why you're doing it. You need to understand why you're doing what you're doing. Now I want to tell you one other thing about this, because this will cause some people to get a little irritated. Usually you'll have a real and imaginary impedance. And on the primary side, you'll have real and imaginary. It'll get more complicated. You gotta be careful with that, because the polar numbers and stuff like this can be an irritant. Another thing that happens is this. Instead of the dot being up here, there'll be a dot here. And that means V2 now would be this. And the current I2 would be this. Do you all follow? Those are typical things that cause mistakes to be made. I just want to make sure I really show light and showcase the things that are typical that will cause problems. Now, that's the second problem. It's really a problem class, and all of them, if you actually look in your book, for these transformer problems, I mean, every single one is basically just more complicated versions of that. Sometimes, if you look on, oh, this is a good one. So, maybe, all right, we'll do 818. This one's a little more complicated, but hopefully, what I'm trying to do is just increase the difficulty in a way that isn't going to cause you to get confused. Did I put that, was that an assigned problem, by the way, or not? Anybody tell me? On OneNote? If not, you should do it. Make sure you know how to do that problem. All right. So 818 is a little trickier, but I think you can figure it out. I think. So they do this. They have, and here I'll show you how you're using everything from before to solve these problems. This is 12 volts at 0 degrees, volts RMS. Then you got 1 ohm, and then you have a current here of 4 amps, an angle of 0 degrees, and that's amps RMS. Then you have this. He likes to put that symbol in. It's kind of a problem. You're going to need more than just a basic understanding of transforms to do this problem. And what was the turns ratio was 1 to 2. So he has 1 to 2 here. Can you all see the problem? In the far back. Okay. So to start a problem like this, it's smart to label where V1 and I1 are until you get to a point where you really understand this. So this is plus to minus V1, And this is plus to minus V2. You'll notice it's inverted because the dots are not on the same side, or they're not both up, both down. One's up, one's down. You all follow me? Next, the current. This is going to be the I1 related to those equations, and this is the I2 related to those equations and the turns ratio. Do you agree with that, class? Obviously, N1 is 1 and N2 is 2. Okay, now I'm going to tell you several different ways you can solve this. And I want you to listen. You remember superposition, right? So we could find V out here if this voltage source was there, but we turn off the current source. Are you listening? And then we could turn off the voltage source and find V out from the current source and add the two together. That's superposition. How many understand? All right, we've covered that some time ago. Some of you might do that. I wouldn't. Another way, a simpler way, in my opinion, and the way, if you've done enough problems, you always do this, is say that these sources can be combined. Y'all hear me on this one? So what I'm going to do is this. I'm going to take this voltage in series with that resistance and give it, that's a Thevenin equivalent, I'll do it a Norton equivalent current source in parallel with that resistance. How many remember that when I did this some time ago? If you don't, make sure you pay attention. These are tricks, and they're tools in your toolkit that you will need to use. You can use superposition, but it's kind of a long thing. So what I'm going to do over here is say, at this point, if I snip this, I can say that voltage in series with resistance would be equal to the current that would flow, if that's a short circuit, in parallel with that resistance. Do you remember this? Some of you do. Okay, so I'm going to say that what happens is now I have a current here. That current would be 12 over 1 amps. And then it would be in parallel with 1 ohm. And there's a second current source here. That current source is given as 4 amps. And here's what the transformer would be. Do you agree with this, class? It's not time to go. Everybody with me? Somebody take me to the next logical step. This is 12 amps. Anyone? How many see those two current sources are in parallel and both shoving current to that upper rail from that lower rail? How many see that? You agree we can combine them, class? Sure. That would be 4 and 12 is 16, so we could say this could be replaced, and it is replaced, by 16 amps in parallel with 1 ohm. Follow me? Now, that can be replaced. Most of you like voltage sources, I think. You don't like parallel current sources with parallel reflected impedance. I'm just, based on past experience, I'm guessing that. I don't like that either. So I take this and make it equal to a series, right? An actual series voltage source of plus to minus 16 volts, right? With 1 ohm. Follow the progression, everyone? So I would normally just, right off the bat, do an equivalent for this. And I'd replace it with 16 volts in series with 1 ohm. And for the sake of time, I'm going to do it right now. Now, let me ask the obvious question. At that point, I'm asking this, how many feel that you can figure out how to get V naught? Over here, guys. What do you need? Well, I need I1. What do you do to get I1? You reflect the impedance of the secondary back here to the primary and add it to 1 ohm. Then you would take that value and divide it into 16. You would have I1. Do you agree? Once you have I1, do you have I2? Class? Sure you do. By the turns ratio, right? Since it's 1 to 2, the current here will be less by a half. Take 1/2 I1. Once you have that current, I can get this voltage by taking 8 times I2. How many see that? But that's the wrong polarity. So I put a negative sign in front of it. You all with me? Now I showed you the trick on that one. I'm going to give you some more homework. Please do this. Next time I'm moving to a new topic. And I'll need you done with this. I'll answer any questions we're doing.